Section 38 of The Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avayi in July 2015. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler. Astronomy. Chapter 25. Cosmogony and Stellar Evolution, Part 1. The striking regularity and uniformity which prevails in the planetary system was a mystery to Newton. He was aware that the then known planets and satellites all move in the same direction, all nearly in the same plane, the ecliptic, and all in almost circular orbits. As Newton did not believe in any vortex movement, such as that suggested by Descartes, to carry the celestial bodies along with it, he could not understand this peculiar regularity, the less so because the comets, whose orbits seemed likewise to be dependent upon the attraction of the Sun, frequently did not at all move in the same direction as the planets. Without any justification, Newton drew the conclusion that the regularity of the planetary movements could not have any primal cause. The first who seems to have aspired to such an explanation was Buffon, the ingenious author of the Histoire naturelle (1745). From the outset he emphasized the extraordinary improbability that the inclination of the ecliptic to the plane of the planetary orbits would, by itself, and merely owing to chance, never exceed 7½ degrees, or 1/24th of the largest possible inclination of 180 degrees. That point had already been accentuated by Bernoulli. The probability that this inclination is mere chance amounts for every single planet only to 1/24th. For the 5 then known planets taken altogether, the probability assumed the value of 24 to the power of -5, or 1/8 millionth. They had to consider in addition that the satellites, so far as then known, namely, the 5 moons about Saturn, 4 about Jupiter, the 1 of the Earth, and the ring of Saturn, were all moving in planes which deviated little from the ecliptic. A mechanical cause had to be found in explanation of these facts. In order to explain the movement of the planets, Buffon supposed that they had resulted from a collision between the Sun and comets. Assuming that a small amount of the Sun's mass was knocked off, he fancied that as the result of such collisions planets and their moons were formed. The possibility of such an impact between a comet and the Sun seemed to him proved by the comet of 1680, whose orbit, Newton had calculated, passed the Sun's luminous surface at a distance of only 1/3 the solar radius, and on its return 600 years later would fall into the Sun. The fragments of the Sun formed from such a collision would not drop back into that body, but would fly off with a rotary motion in the same direction. The fragments which possessed the smallest density would attain the greatest velocity, and would therefore be hurled farthest away from the Sun before their orbits began to curve. The enormous heat produced by the collision would probably render the planets liquid, but they would rapidly cool owing to their small size, though remaining incandescent for longer or shorter periods. Thus to the Earth Buffon assigned a period of 75,000 years for cooling down to its actual temperature, for the Moon 16,000 years, for Jupiter 200,000, and for Saturn 131,000, while the Sun required 10 times as long again as Jupiter. In passing through the atmosphere of the Sun after their separation, the planets would absorb from it air and water from which seas would later on be condensed. This atmosphere would resemble that of the Earth, for, except that he thought the Sun was a solid incandescent body, Buffon regarded it as otherwise resembling the Earth in its essential characteristics. The Earth he considered had ceased to be incandescent because no air could penetrate into it to feed the eternal fire. Yet at the same time he believed that only 2% of the terrestrial heat was due to the radiation from the Sun, the remainder being the Earth's own heat. Buffon's theory was followed by that of Thomas Wright, whose hypothesis of the evolution of the universe as well as the solar system, published in 1750, supplied an approximately scientific explanation to the whole sidereal universe. According to Wright, the solar system is but one of a vast number of such gravitating systems which form the Milky Way. These are arranged in a great double ring, forming a stratum or disk of stars, which rotates about an axis perpendicular to its plane. The ideas of Wright met with the approval of Immanuel Kant, who in 1755 explained his theory of the evolution of the solar system. According to him, cosmic space was empty, and the planets could not be carried through it by any vortices in the sense of Descartes. But, provided the planets had once been set in motion, no other impelling force was needed for them in this empty space. Why could it not be assumed that the vortex which had started these planets on their trajectories had once existed and disappeared afterward? Kant then states that in the beginning all the matter which is now in the Sun, planets and in the comets must have been spread through the space in which these bodies now circulate. The attraction of the particles was directed toward the center of this mass of dust, where the Sun stands now. The material particles at once began to fall toward the center of the mass. Thus resulted movements in closed paths or circular orbits about the center. As the different bodies collided with one another, they eventually grouped themselves and moved in circular paths in the same direction about their common center. Some of the bodies which were falling toward the center would likewise assume the same movement and would cause the Sun to rotate about its axis in the same direction. Kant maintained that the central body would be specifically lighter than those nearer to it. In this respect he was in error, as we see in the case of the Earth and the Moon. Kant advanced various explanations for such points as the deviation of the planetary orbits from circles and their inclination to the ecliptic, for the formation of Saturn's rings, for the interpretation of the deluge and other biblical facts. Finally he explained the extinction of the Sun, which, according to the view of that age, was a celestial body in the process of burning. The end of the Sun was destined to ensue from want of air and from accumulations of ashes. In this process of burning the Sun had lost its most volatile and finest particles, constituting the cloud of dust which he assumed to be the seat of the zodiacal light. Kant makes the significant observation that the law concerning the extinction of the Sun includes a germ for the reunion of dispersed particles, even if the latter should have intermingled with the chaos. This is interesting as indicating that matter passed through a cycle of evolution, being now condensed into suns and now scattered into chaos, the idea partaking somewhat of that advanced centuries before by Democritus, who believed that matter was in constant motion and that the atoms were eternal and indestructible. In short, the cosmogony of Kant is typical of those theories which assume the planetary system to have originated from cosmic dust or from a collection of small meteorites. In more modern times, ideas based on this hypothesis have been advanced by Nordenskjöld and Lockyer, while Sir George H. Darwin has devoted much thought to the mathematical consideration of such a theory. Few philosophers or astronomers were in a better position to frame a basis for cosmical theory than Laplace, whose work in this field must be mentioned after that of Kant. At the end of his Système du Monde (1796), he advances a mechanical explanation of the evolution of the solar system, accompanying it, however, with the explanation that it had not been subjected to rigorous mathematical analysis and proof, and was advanced in a more or less tentative way. Despite the hesitancy with which Laplace offered this contribution to cosmical theory, it soon secured wide consideration, and was found acceptable as a fundamental basis to explain the origin and evolution of the universe. In fact, this nebular hypothesis was, without doubt, during the 19th century the guiding idea in cosmical philosophy, as well as the philosophical basis underlying astronomy. The work itself has been likened very properly to that of Charles Darwin. Laplace starts with the assumption of a glowing mass of gas which, from the very first, was in vortex motion from right to left, as viewed from the north, about an axis passing through its center of gravity. In its primitive assumed condition the Sun resembled those nebulae which are shown by the telescope to be composed of a more or less brilliant nucleus surrounded by a nebulosity which is condensing upon the nucleus, transforming it into a star. The solar mass cannot have extended out indefinitely. Its limits were the points at which the centrifugal force, due to its motion of rotation, were balanced by the gravitation of its action. On cooling, the nebulae would contract, and in this contraction of the glowing mass of gas a gaseous disk would be split off, when the centrifugal force of the rotating mass would be equal to the inwardly directed force of gravitation, so that the solar nebulae were divided into rings of glowing gases which would rotate as a whole and cool down in a solid or liquid ring. Laplace says: "It may be conceived that the endless variety in the temperature and density of the various parts of this great mass produced eccentricity of their orbits and deviation of their motion from the plane of its equator." Laplace mentions the presence of comets, which he states are strangers to the planetary system, as colliding with the planets during their process of formation and causing them to deviate, while other comets entering the solar system near the condensation of gaseous matter, so nearly completed, became retarded in their motion and were incorporated into the solar system. His conclusion was as follows: "Whatever be the masses of the planets, it is only owing to the circumstance that they all move in the same direction and in almost circular orbits, at small inclinations to one another, that the secular variations in their orbits are periodical and within narrow limits, and that the system therefore oscillates about a mean condition, from which it never deviates by more than an insignificant amount." While Laplace's theory was open to criticism and objection at numerous points, yet it played a useful and remarkable part in the development of science. The Newtonian doctrine of the wonderful stability of the solar system was more firmly established, and the permanence of the planetary system was guaranteed. While it was confined only to the solar system, yet the idea of the nebular hypothesis was readily applicable to the universe itself, and formed what long was considered a satisfactory means of accounting for its origin and evolution. In its mechanical aspect, Laplace's idea of the segregation of small dust particles during the cooling of nebulae and their aggregation by the condensation of gases into a ring or a single big mass was found physically impossible by later astronomers, notable among whom were Stockwell and Newcomb. There would result, on this hypothesis, a collection of small meteorites, such as circulated in the Saturn rings, and the transformation of the Neptune belt into a planet would have required no less than 120 million years. The retrograde movement of the moons of Uranus and Neptune, and also that of the most remote moons of Saturn and Jupiter, formed another serious objection to the thesis of Laplace. The first important cosmical theory seriously to modify the nebular hypothesis of Laplace was that first presented on November 17, 1887, by Sir Norman Lockyer. This was known as the meteoritic hypothesis, and in its more complete form was published in 1890. The fundamental principle involved in this theory was that all self-luminous bodies in celestial space are composed either of swarms of meteorites or of masses of meteoritic vapor produced by heat. This theory was the result of spectroscopic studies. Lockyer claimed that the original nebulae were composed of meteoric material or cosmical dust rather than gases. In other words, nebulae were vast swarms of meteors, and their light resulted from continual collisions between constituent particles. Such a collision might take place between two stars, shattering both and producing a vapor or vapor combined with meteoric fragments from which other stars might be derived. Thus, a dark star might be transformed into a bright and glowing star, and pass through successive changes until it was dissipated by some long delayed collision. Lockyer assumed that the meteorites could be regarded as analogous to wandering molecules of gas moving indiscriminately in all directions and at widely different velocities. He believed that the heat produced by the collision already referred to would volatilize certain constituents of the meteorites and render them luminous. These luminous materials would supply a spectrum, and the discussion of the properties of the spectra of nebula was an important consideration in Lockyer's work. In some respects this theory has been found untenable. The meteoritic hypothesis was never considered seriously as supplanting the fundamental ideas involved in Laplace's great generalization. Sir George H. Darwin, whose work on the tides has had considerable bearing on cosmical theory, also discussed the physical and mathematical properties of the meteoritic swarm, and demonstrated that its behavior closely resembled that of a gas, and that the meteorites would move about, colliding with one another in much the same fashion as the molecules of gas according to the kinetic theory. Darwin further demonstrated that when a mass was widely extended it would revolve as a solid. But such ideas as those of Lockyer and Darwin involved modifications of the nebular hypothesis rather than an overthrow. End of section 38.